Ever wondered how your computer manages to run multiple applications at the same time? Well, let's unravel this mystery by introducing the concept of threads. Threads are the smallest units of execution within a process. Imagine a process as a factory, and threads are the workers in that factory. Each worker, or thread, has a specific task to perform, but they all share the factory's resources. In the case of a computer process, these resources might be memory, file descriptors, and I/O devices. A process can have multiple threads, all executing different tasks but sharing the same resources. This is how a single process can perform multiple tasks simultaneously. And when you have multiple processes, each with multiple threads, that's when the real magic happens. That's how your computer can run multiple applications all at once. So, in essence, threads are what allow your computer to multitask effectively. But how does a thread come into existence? It's a fascinating journey. In the realm of operating systems, threads are birthed within a process. This creation can be facilitated by the operating system itself, or the process can take charge, employing threading libraries or application programming interfaces, commonly known as APIs. Now, these APIs are the tools provided by the operating system. So in essence, the process has a choice to either let the operating system handle the creation of threads or take matters into its own hands. It's quite the collaborative effort, isn't it? But regardless of who initiates the creation, the newborn thread is not alone. It shares the same address space and other resources with its sibling threads within the process. So when a thread is created, it's ready to share the same address space and resources with other threads in the process. Threads are not just simple units of execution, they come with their own set of attributes. And these attributes are not just trivial, they play significant roles in how a thread functions. Let's delve into the unique characteristics that threads possess. First up, we have the thread ID, or TID. This is a unique identifier assigned by the operating system. The TID differentiates each thread within a process, serving as a distinct name tag of sorts. Next, we have the state of the thread. This attribute indicates the current stage of execution. Threads can exist in different states such as running, ready, blocked, or terminated. The state of a thread can change throughout its life cycle, reflecting the thread's progression. Then there's the stack. Each thread has its own stack, a private space for storing local variables, function parameters, and return addresses. Think of it as a personal notebook where a thread jots down important details while it's working. The program counter, often abbreviated as PC, is another crucial attribute. This keeps track of the currently executing instruction within the thread. It's like a bookmark that helps the thread remember where it left off in the sequence of execution. Lastly, we have the registers. Threads have their own set of CPU registers, including the instruction pointer and general purpose registers. These registers hold temporary data during execution and are instrumental in carrying out operations. In essence, these attributes are the building blocks that shape a thread's identity and functionality. They enable the thread to execute tasks independently within the same process, allowing for efficient multitasking. So the next time you think of threads, remember they're not just a simple sequence of instructions. They're sophisticated units of execution, each with its own unique identity and attributes. Each thread is like an individual performer in a grand orchestra, playing its part in harmony with the others, yet standing out with its unique characteristics. These attributes are what make each thread unique and capable of executing tasks independently. So, how does the operating system decide which thread to run when? Let's dive into the fascinating world of thread execution and scheduling. Thread execution is a dynamic process. Within a single operating system process, multiple threads can execute concurrently or in parallel. The concept of concurrency allows threads to progress simultaneously, while parallelism takes advantage of multiple CPU cores to execute threads at the same time. This shared memory space allows threads to access common data and communicate more efficiently than independent processes. But how does the operating system manage all these threads and ensure they get their fair share of the CPU? Here enters the concept of thread scheduling. Thread scheduling involves selecting threads from the ready queue, which is a holding area for threads that are prepared to run, and allocating CPU time to them. The scheduling algorithm used by the operating system plays a crucial role in this. Different algorithms have different objectives. Some aim to optimize system performance by maximizing throughput, which is the amount of work done in a given time. Others focus on minimizing response time, trying to ensure that every thread gets a quick turn on the CPU. Fairness is another critical aspect of thread scheduling. It's all about ensuring that all threads get their fair share of CPU time. In a fair system, no thread should be left languishing in the ready queue for too long. However, scheduling isn't just about fairness, it's also about balance. The operating system must balance the need for efficient resource utilization with the need to meet the performance expectations of the users and applications. So, in a nutshell, thread execution and scheduling is a complex dance orchestrated by the operating system. It's about managing resources, balancing competing demands, and ensuring that all threads get a chance to perform their tasks. This dance, when done right, can result in a system that is efficient, responsive, and fair. So the next time you're multitasking on your computer, spare a thought for the intricate ballet of thread scheduling happening behind the scenes. Thread scheduling is all about optimizing system performance and ensuring fairness among threads. Threads don't just execute tasks, they revolutionize how tasks are performed. Let's delve into how threads enable concurrency and parallelism, transforming the realm of multitasking and supercharging performance. Imagine threads as jugglers, each juggling multiple balls, those balls being tasks. Now, if a juggler is particularly skilled, they can keep several balls in the air at the same time, never missing a beat. This is the essence of concurrency. Threads, like expert jugglers, keep multiple tasks progressing simultaneously within a single process. They switch between tasks seamlessly, giving the illusion of simultaneous execution. This is particularly useful when tasks are independent or when one task must wait for an external event, like user input or data from a network. During the wait, the thread can work on other tasks, optimizing the use of time and resources. But what if we have more than one juggler? Better yet, what if these jugglers could work together, throwing balls to each other in a coordinated fashion to keep even more balls in the air? This is parallelism. Threads can execute tasks concurrently across multiple CPU cores, like a team of jugglers working in unison. This takes full advantage of multi-core processors, significantly improving performance. With parallelism, tasks are completed faster as they are literally being done at the same time. However, it's important to remember that while concurrency and parallelism can greatly enhance performance, they also add complexity. Just like juggling requires skill and coordination, managing multiple threads requires careful programming. We must ensure tasks are properly synchronized and data is safely shared to prevent issues like race conditions or deadlocks. Ultimately, threads bring to life the concept of doing more with less. By enabling concurrency and parallelism, they allow for efficient multitasking, making your programs run faster and smoother. They ensure that your computer's hardware resources are not just utilized, but optimized, squeezing every bit of performance out of them. Threads therefore make the most out of your computer's hardware resources. Threads within a process must communicate, but how do they do it? And what happens when a thread's job is done? Threads communicate using two primary methods: shared memory and synchronization mechanisms. Shared memory is just as it sounds, memory that is accessible by all threads within a process. This allows for direct and efficient communication. Synchronization mechanisms, on the other hand, are tools provided by the operating system. These include mutexes, semaphores, and condition variables, which help threads to coordinate their actions and avoid conflicts. Now let's talk about termination. Threads can come to an end in two ways. First, they may complete their execution. This means they've done their job and simply stop running. Second, they can be explicitly terminated by the process or the operating system. In either case, upon termination, the resources associated with the thread, like stack space and thread-specific data, are deallocated. So threads communicate efficiently and terminate cleanly, freeing up resources for other threads. So we've taken a journey through the life of a thread. We've seen how these lightweight units of execution are born within a process, each with their unique thread ID and state. We've discovered how they each possess their own stack, program counter, and set of CPU registers, all while sharing the same address space and resources within a process. We've witnessed the dance of execution and scheduling, where threads take turns under the spotlight of the CPU's attention. We've marveled at the synergy of concurrency and parallelism, where threads enable multiple tasks to progress simultaneously, Optimizing performance on multi-core processors. We've seen how threads communicate through shared memory and how they gracefully bow out upon termination, freeing up resources. Threads truly are the unsung heroes of multitasking, concurrency, and parallel programming. They keep our applications running smoothly, making the most of our hardware resources. Remember, threads are the unsung heroes that keep your computer running smoothly. Thanks for joining me on this exploration of threads in operating systems.